Hey, morning. Let's start the lecture. Okay, so we'll continue on the open loop pulse transfer function, and then today we'll talk about closed loop. But there is a concept. Let's just quickly go over. This is a control system concept, of course. This is basically it's called concept of DC gain. Okay, so DC is basically the versus the AC. Okay. So DC gain essentially we call it steady state gain. Okay, yeah, or it's a ratio of the output of the system, okay, then to its input. At steady state. So often in time, what we compare is we compare step input and then look at the output of steady state. The ratio of that gives us the DC gain. Okay, it's DC gain. The reason that DC gain is important because you see the way you put step input into a system, and when you look at the output, you want the output generator to follow the inputs, right? Yeah. If the output is not following the input, which means the output is not 1, then there will be a non-constant 1 DC gain in the system. And when that happens, then that means that we have a system that there will be steady state error, right? Yeah. Okay, so we're basically dealing with discrete system. So let's say I'll give the example that we will be dealing with here. Let's say we have a zero order hold. And then we have a plant. So it's a pretty simple system. And this is together we can call it G of S, right? And we have an input, let's see, unit step function. Then we have an output. Okay, so we're going to, if we're going to look at the DC gain, basically, first step is actually you need, we're looking at discrete ones here. So typically, what happens is what we look at is basically C of Z, right? Yeah. So this is the unit step function input. The unit step function input, if you look at the Z transform, it's Z over Z minus 1, right? Yeah. So from the definition, DC gain is the output of the system over the input. Output of the system at the steady state. Output of system at steady state. If you remember when we learned the Z transform, there are two property or two theorem, right? One is initial value theorem, the other is the final value theorem. And the final value theorem tell you what? Tells you what the value of that the inverse that function is, right? At the infinite or at the steady states. Okay? So basically what we need is what's the steady state, what's the final value, right, for this guy here. Okay? If we know the steady state value or the final value is, then divided by the input, which is 1, then you get your DC gain. Okay? Yeah. So in other words, your DC gain basically equal to this C function here at steady state at infinite. Okay? Infinite. So final value theorem. So final value theorem, if you remember what's the final value theorem, it's Z approach to 1, right? Z approach 1, and then y minus Z to the power of -1 C Z. Okay, that's final value theorem. Okay, so in this case here, what is the CZ? So CZ equal to this GZ times the unit step input, right? Yeah. Okay, so CZ is the GZ. So GZ is the Z transform of these two blocks and times the step input. Okay. Yeah. So now let's simplify this a little bit here. Okay. Yeah.
Didn't at the beginning of the lecture say though that DC gain was the ratio of the output over the input?
Yeah, output over the input.
So in this bottom one now you're just saying that it's just the output.
Right, because the input we're comparing the unit step input. Right? So basically the magnitude of the input is 1, right?
Yeah.
Okay, so just a simple simplification here. And this is Z minus 1 over Z is actually, you see, they cancel this guy here, right? So basically you end up with you just end up with this one here. Okay? Yeah. Or in other words, and just this guy. Okay? That's the DC gain. Is that good? Yeah. Continuous system also has a DC gain concept. So let's say if you have just a plant, and you want to know what is the DC gain for the plant. What you do is just let S go to 0. Okay, and that's the DC gain. And this is for continuous system, right? Yeah. Okay. So, pardon me?
That's the initial value?
Initial layer. The same idea, basically. This is the plant, right?
Why is it going to 0 this time?
Oh, that's basically the final value theorem for
estimate.
for continuous system. Yeah. Right. So if you have a unit step input, what's the output, right? And basically, okay, same idea. Okay. So let's see a very simple in one example. In one example in the previous lecture, and I put this GP of S. Let's see, what did I put? I put GP of S here. So I said this GP of the plant is 1 over S plus 1. Okay. And plant is this. And let's say in this particular case, what will be the DC gain? Okay. Yeah. Okay. So if GP of S is 1 over S, okay, 1 over S plus 1, and we're able to derive basically that G of Z, okay, which is Z transform of 1 minus E over TS over S and GP of S. Okay. So it's the Z transform, okay, of the plant, but with a 0 order hold in front of the plant, right? If you look at some of the textbook here, for this kind of Z transform, basically it's particularly the zero order hold in front of it. This is also called step invariant Z transform. Okay, step invariant transform. So why step invariant? Because this is the 0 order hold, right? So there's a step, every step there's no change within that interval. Okay, yeah. So incidentally, if this is called step invariant Z transform, if you simply have this, let's say Z just GP of S, if you're just looking for Z GP of S, you know, that's basically what's in the table that you have, the Z transform table that you have, right? This is called impulse, okay? Impulse invariant Z transform. Or something, just call it impulse Z transform. Okay, yeah. A subtle difference. But anyhow, for this particular case, I want you to remember, right? I want you to remember, you don't need to go over every step, but you should know that whenever you have a zero order holding from the plant, the Z transform here is Z minus 1 minus Z to the power of negative 1, and Z 1 over S GP of S. Okay, so that's what you need to remember. Okay. So the second one here, this block here, you can use a table to find its Z transform, right? Yeah. So for this particular case, this is 1 over S, okay, S plus 1, so you can find that easily. We find that in our case is 1 minus this, Z minus this, right, in the previous lecture.
So just to repeat what you're saying there, is whenever you have a zero order hold, which is the 1 minus 2 x over S,
yeah, plant, yeah,
you can go right down to that.
yes. Yeah, so basically, whenever you see that, the Z transform, the multiplication of these two things, right? You don't need to know how this is from here, but you need to remember now, right? Because of course you can derive that, which is basically this. Yeah.
And then you can go to your tables with
Exactly. Yeah, for this one here. Okay. Yeah. Okay. So this is your G of Z, right? So let's go back here. So what we're looking for is DC gain of the system, right? DC gain when the system input is a unit step input. So basically G of Z in this formula here, okay, this is G of Z. You might have something else, okay? So this is simplified system. You might have I don't know, maybe another block or it's a closed loop system, right? But this is just for this one. Okay, so let's see what's the DC gain here. So DC gain. Limit. So according to the definition of DC gain, so DC gain basically equal to the G of at Z equal to 1, right? Equal 1. So what do we do? This is G, so G at 1. So what do we end up with? Sorry. Oh, that example. Yeah, that example has a controller in an example. But anyway, let's try this one here. Okay, suppose this is my system. Okay, G of 1 here. So what's G of 1? So 1 minus this over 1 minus this, right? Okay, which is 1, right? Which is 1. So what does that tell you? Basically, if this is the system here, right? If you give a unit step input to it, then at the steady state, the system will reach 1, right, at a certain instant. So there won't be any steady state error. Okay, so this is actually, you don't need to control it. See, right? Yeah. If you don't care about the response time, and basically the system will respond to the unit step input perfectly. Is that good? Yeah. So that's the concept DC gain, right? Yeah. Okay, so let's move on from here. Now let's look at closed loop. Okay, pulse transfer function. Okay, closed loop. Okay, so let's start from an example here. Okay. Of a generic diagram. Okay. Okay, so let's say I have let's put a block here. I have a closed loop system. Okay, it's a sample data system. Basically, it's a mix of continuous and discrete blocks. Okay, yeah. So the input is R of S, reference input. Negative feedback. Output is Y of S. Okay. Yeah. So you know that what's out of the block here is the error. Okay, yeah. So this is an impulse sampler. Okay, this is impulse sampler here. So anything after the impulse sampler, if you remember, so instead of E of S now, we call that what? E star of S, right? Yeah. Okay, so that's it. That's the block here. So what will be the pulse transfer function for this closed loop system? So in other words, what you're looking for is what's Y of Z over R of Z, right? Yeah. So the confusing part a lot of time is, so where's Y of Z? Is that R of Z here in this case, right? Well, all you see is continuous Y of S or R of S, right? But you can always, remember, you can always put in a fictitious impulse sampler here to get you Y star of S. Okay, so that impulse sampler doesn't really need to exist, right? Yeah, it's a fictitious one as you put in the term of programming. So practically you don't need that there, right? Okay, so when you try to find closed loop pulse transfer function, this is what you're trying to find. And Y of Z over R of Z, if you remember that, okay, basically you need to find this. Okay. Once you find this, you can simply change the S to Z. Well, it's not the direct change, but you can, in terms of the replacement, is 1 over T log Z, right? Yeah. But we know that the Y of Z, any Z function signifies is this start Laplace transform, right? Okay. So this is what we need to find here. Okay. And just like a continuous system, how do you find the transfer function of a continuous system? So basically, often in time, you just have to start from the E of S set here, right? And going through the block by multiplying things or adding things together, and then in the end, you find a relationship, a ratio between Y of S over R of S, right? Yeah, so very similar. So let's see, what do we do at here? So E of S, okay, so this error equal to the reference minus whatever this signal at here, right? Signal here. And the signal over here equal to what? Equal to this block times here. And that signal is Y of S, so H of S times Y of S at here. Okay? Yeah. And what's Y of S then? And Y of S equal to, this is output, Y of S equal to the signal E star times this block G, right? E star times G. So basically it's this block G of S times E star of S. Okay? Yeah. Okay, so right away we can manipulate based on these two expressions now. Okay? I can replace this Y of S, replace the Y of S basically with G of S times E star. Then my E of S equal to R of S minus H of S times G of S times E star of S. Okay. Is that good? Yeah. Okay, so at this stage at here, remember, this is your objective here, okay? This is your objective. You want to find the ratio between Y star and R star, okay? Yeah. Then, what I can do is, I'll combine these two together, okay? So, this HG at here, I'll call this just one GH of S. Okay, is that good? Yeah. Then this expression E of S equal to this. I'll take, remember the action, I'll take the start Laplace transform of both sides of that equation. Okay, so what it means is I take the start operation, okay, of both sides of this equation. Okay. So if we do that, we get E star of S equal to R star of S. See, R star of S shows up now, right? Minus GH star of S. Star star still the star, so no change. Okay? Yeah. So you see the reason why we're combining these two into one block, right? Because that's the properties of star operation. Okay? Yeah. If you don't do this step, you take the star, that doesn't necessarily gonna give you H star G star. Okay? That's a mistake. Okay? Yeah. Okay, so now we can simplify this a little bit. So we get what? E star of S equals, so move this whole chunk over there and take out the common factor, and we get 1 over 1 plus GH star of S times R star of S. Okay? Yeah. So that's E star of S. And you have the R star of S showing here specifically, okay, explicitly. Is it clear from here to here? Yeah. So now the next step I'm going to do is, from this expression here, this expression, I have R star now, right? But I haven't got my Y star yet. So at this expression here, I'll take the star operation of both sides, and I'm gonna get what? Okay, yeah. Is that good? Yeah. So let me write down that expression down here. Okay. So these two together, right? We can find the ratio between Y star over the R star. Okay. So what's the ratio? So what do? You basically substitute the E star from here over here, and then find the ratio, right? Yeah. So that gives me the ratio Y star over R star, which is G star over G star times, G star over what? GH star S. Okay, yeah. So that's this ratio between these two star Laplace transform. But you need Y of Z over R of Z. So last step is pretty easy now. We don't know what exactly each function are, right? And what we just, in this case, what we do is generic expression. So all we need is just change the S here with the Z. Okay, so basically Y of Z over R of Z equal to G of Z over 1 plus GH of Z. Okay, yeah. So you might want to ask, well, how do I get a G of Z, or how do I get a GH of Z, right? Well, what's the G of Z? G of Z, you know what the G of Z should be what? The Z, the G of S, right? You have two different ways to do it, right? You can use table, you can use the basically from G of S to G star first by finding the residual on assignments, right? And then do a replacement to find the Z function. Okay? Yeah. This is the closed loop pulse transfer function. Okay. Yeah. Okay, so for now, I'll tell you the trick shortly, but let's just say if you don't have the impulse sampler and then becomes continuous system, right? Okay, what's the closed loop transfer function for the continuous system without in the impulse sampler? The same? What do you mean the same? For continuous one, you should remember all this. Yes. right? That's continuous one. Okay, yeah. So first observation, but I'll tell you how. But the first observation between these two here, okay, between these two, they're not quite the same, but in terms of formality here, this is g of s times h of s, but this is not g of z times h of z, right? And this is what? This is a gh of z. Okay? See the difference between these two, right? Yeah. So I'll tell you the difference, but there is a shortcut here. But just first of all, let's see the difference, okay, between these two. Okay. So second of all, okay, the other fact that you also should know that is the closed loop pulse transfer function doesn't necessarily exist for all cases. Okay? Doesn't exist means what? Means you couldn't find a specific or explicitly an expression for this ratio, or in other words, for this ratio. You see what I'm saying, right? So I'll put it here. So closed loop, okay, PTF, okay, may not exist. Okay. So you can take a look at page 112 of textbook, okay, to see what kind of a system doesn't exist. But the rule of thumb that to see whether it exists or not, there's a very simple rule of thumb is if there is no impulse sampler, right outside of this subtraction junction, okay? If there's no such thing right after this subtraction junction, then chances are you don't have this closed loop pulse transfer function. Okay, so let me show you one block at it here. Okay, if no delta t, okay, after the junction here, the subtraction junction, okay, no PTF. Okay. So you can try this. Let's say I have a closed loop system like this. Okay, so if there's a closed loop system, you see this impulse sampler, okay, not immediately following this subtraction junction in this case here. What you can do is you can try exactly what we just gone through, this, all the blocks and all the star things, giving at each location, right? You won't be able, actually in this case, you won't be able to obtain explicitly a ratio, okay, which is a pulse transfer function. Okay, so you won't be able to do this. Okay, that's basically because this guy is not directly following it here, right? Okay, so let's take a look at a specific example here. Basically, it's very similar to the example for the open loop one. So remember this block, that's open loop, right? So now I'm going to close the loop at here. Okay, so we close the loop. Okay, and then let's look at what's the closed loop pulse transfer function for this system. Right, so the only difference is close the loop now. Okay, so in the previous lecture, actually just 10 minutes ago, we if I call this is g of s, we derived the g of z already, right? We derived the g of z. So that's basically 1 over this, okay? That's g of z. Okay. Now, according to the block that I used over here, so h of s in that example is actually just 1, right? And g of s is this guy here, okay? So then my closed loop pulse transfer function should be g of z over 1 plus, instead of gh, this is actually just what? G of z, okay? Yeah. So what we're looking at is this one, okay? Yeah. Put them together, we get so this is what we get. Okay, yeah. All right, so in the future we're going to learn basically as stability of the system. Now, in terms of stability of the system, so let's very superficially touch upon that issue right here. Yeah,
I just have a question. You go up a little bit. When you push h of s and g of s together, you call it g h of s.
Yeah. This, you mean this one here?
Yeah.
Like this?
Yeah. Is that because you know that the impulse sample is right in front of the subtraction junction, therefore you can do that?
Well, for these steps here, let's just see. Basically, this is a mechanical following. Anything. Even if you don't know this rule of thumb, right? Even if you don't know this rule of thumb here, you can always follow things just like this, right? But the reason I'm putting these two together into this, from this step to this step here, is because this step. Because the next step I'm trying to do, I'm trying to take the start operation of the E star here, right? If I'm trying to take the start operation both sides of this equation, and I know that for start operation, so basically what I'm saying is, if you have, let's say, A1 of S, A2 of S, and A3 of S, okay? When you take the start operation like this, you don't get this, this, and this. You don't get this, okay? What you get is, right, the only property that applies, okay, is only two of them. Okay, there's only two of them, and then you get this. That's okay. Okay, you have two of them, right? So you see, there's three of them here, right? If I take the start of Laplace here, I'm gonna have to combine things together, in order to get everything in the start, right? So I don't want to mix the S and the start S together. Start S is actually basically the discrete or sample ones, right? And then this S one is the continuous one. Okay, so this is why I put these two together here, right? Yeah. Okay. All right. So, very preliminary, when we're dealing with the stability of the system. Now, what you need to look at is, if you look at your Z table, okay, if you look at your Z table, okay, so particularly, let's just say a transformation between these two and these two here is actually they're equivalent. Okay, you can always write into equivalent format here. Okay, you look at these two here. If you have a Z transform function like this, okay, if you have a Z transform like this, then you know the inverse is going to be either this or that. Doesn't matter, right? It's basically exponential things. Okay. So, which means what? Which means if you have something like this, and you know this is going to be like that, right? Now, when we do the inverse Z transform for a particular, pulse transfer function, it may not be as simple as this. Maybe, there are different poles. There are multiple poles there, right? But you can always use the partial fraction expansion to simplify that into different portions, okay? Different component, adding them together. But ultimately, right? Ultimately, let's say you have 2 poles or you have 1 pole. Ultimately, the inverse of this is going to be basically a to the power of k, and a at here is what? Is the pole, right? Is the pole here. So if you just look at this one here, then the stability is purely based on the location of the pole, right? Just like continuous system. And for continuous system, when you have the pole location, S domain, and you have learned where do you have the stable region for the pole? It's on the left side, right? But then for the Z here, if I wanted to have a stable response for the discrete system, and this A value has to be what? Within what? Less than 1, right? Less than 1. So basically, the idea is you can try it, right? If a is 3 to the power of k, increase the k from 1 to 2 to infinite. This is going to be keep going up, right? And if a is, let's say, 0.5 of k, as k is going up, it's decreasing, right? Now, if a is negative 0.5 of k, that's okay, right? Yeah. But what would be the difference now? What would be the difference between these two? I mean, but both of this, right, will always decrease to 0 as k go to infinite. Okay. So, in other words, as long as the absolute value of a, okay, is within is less than 1, then you have a stable case. Okay. And that's actually what we're going to learn. Basically, when the poles of the discrete system is within where? Within a unit circle, right? Yeah, for discrete, your DSP, you learn that. Okay. Yeah. And this is actually closely related to the left side of domain of S. So in one of the courses, we'll learn mapping from S to Z, or from S to Z. Okay. Yeah. And the other thing, also trying to just talk for now, is the difference between these two here. So one pole is positive, the other pole is basically, okay, for this one here is Z minus 0.5 over Z. This one here is what? Z over Z plus 0.5, like this, right? Okay. So if you plot these two sequence of numbers here, for this sequence number, it's probably, basically it's going down like this, right? But for this sequence number, because there's a negative, so initially maybe here, and then the next one becomes negative, then positive, negative, positive, negative, positive, like this. That makes sense, right? Yeah. So in other words, for this one here, and compare these two, okay, if you think of a system response, so system response, positive and negative, positive, negative, positive, negative, right? Yeah, like that. Okay. And typically, you don't want that to happen, isn't it? Right? Because if you're controlling the motor, so basically you're giving the motor one mode is positive, the next mode is negative, and you have a very fast rate of a change. That's very confusing. It's very damaging to the motor. Okay. Yeah. So for this particular system, for this closed loop system, where's my pole? Here's my pole here, right? This is my pole. Okay. In other words, if the pole here is -1 plus 2 times e to the power of negative t, okay, that's the pole. And as we said, we want our pole, right? We want our pole to be less than 1. Okay, we want this to be less than 1. Okay. If we want it to be less than 1, and mathematically this means this guy less than 1 and this guy greater than -1. Okay, so absolute value less than 1 means this. Okay, so a little simplification. -1 moved to the other side is 0. And -1 moved to the other side, it's 2. So altogether 1, right? It's 1. Okay. So what is the drawing of e to the power of -t? How do you plot e to the power -t? Give a different value of t. When t is 0, it is 1, right? When t is become bigger, what do you get? You get a bigger value or smaller value? Yeah, you get smaller value, right? Yeah. And you're not going to get the negative, right? So which means the condition I just wrote it here is actually what? It's a natural condition, right? Yeah. So it's naturally satisfied, basically. Or in other words, the pole for this system is always less than, basically less than 1. Okay? So it doesn't matter what sampling time you choose, right? Doesn't matter what sampling time you choose. You always have a stable system, basically. Okay? Yeah. Okay, so there are always certain guidelines in terms of picking up sampling time. It depends on the application. Okay, it depends on the application, and also depends on what you're compensating. But there's always a rule of thumb that's a little bit different. In my lecture notes, I said 5 to time. So sampling time needs to be 5 to 10 times of the bandwidth, okay, of your system, closed loop system. Okay. In some part of this lecture reference, you probably see is actually maybe it should be 10 to 20 times of the bandwidth of your closed loop system, right? Yeah. So that's fine. Oftentimes you gotta just have to play around with it. Okay. Okay. So now I'm gonna let you into a little trick here in terms of deriving the pulse transfer, closed loop pulse transfer function. All right. So here is I'll give you an example first. Okay. Okay, so here's a closed loop sample data system. Okay. There are two pulse samplers. Okay, yeah. So assuming they all have the same sampling frequency. Okay, and actually, you could have a different sampling frequency sometimes. Okay, yeah. Okay, so what will be the closed loop? Okay. Pulse transfer function for this system. Now, I'm not going to go over the steps that as I did in the first example, right? So, what's the procedure I did in that example? So basically, I put down the notations at each critical point. For example, this is E of S. This is going to be E star of S, like that, right? Yeah. And this is the error. This is error. This is what signal is here. So basically, you go over the loops and you find the ratios, right? Okay, yeah. So here's a trick here. But of course, first of all, when you look at this one here, there is an impulse sampler right out after this junction here, right? So which means we will have this pulse transfer function. So it does exist. Okay. And the other thing is, the trick is I'll just write it down in here, okay? Yeah. If there is no, this is not the first step. So the steps here: first derive the continuous Okay, first derived continuous system transfer function. Okay, first derived continuous transfer function. Okay, so let's say what is my continuous system transfer function for this one here, which is what? Which is y of s over r of s equal, what is that equal to? Continuous, get rid of these two. Okay, yeah. Okay, Sandoval, maybe before I move on to the trick here, what's the difference between this example and this example? Well, you know there's there's an impulse sampler. The difference is what? There is an impulse sampler here, right? In the second one, so that that impulse sampler, this one here, it separates these two. Okay, it separates these two. That's the difference, huh? Yeah. And this is actually the second things that you can make use of. If there is a sampler or impulse sampler, okay, separating the S block. Okay, S block meaning not just one, maybe actually two or three as a block. All right. Yeah. If they separate an S block, all you need to do, okay, is basically just to change the S function to Z function. Okay, all you need to do is change the S function to, but that has to, there is a Z sampler, impulse sampler separating the two blocks here. Okay, yeah. So, for example, here, between G of H, there is an impulse sampler separating these two, right? Now, if we want the closed loop pulse transfer function, so for that particular system, which will be what? Y of Z over R of Z equal. So what do we do with the G of S? Change that to G of Z. Now what do we do with these two? Because there's a sampler between the two blocks, right? So all we can do is just change that to each of the Z function. If there is no impulse sampler separating the two blocks, okay, so basically if no, okay, if not, what do you do? Just like this one, there's no, so what do? You are combining the two blocks into one block. Okay, so combine those S blocks. Okay, combine those S blocks until where? Until the next sampler, shows up. Okay, so basically, like here, there might be another S block here, another S block, right? So all you need to do is just combine everything together until here. Okay. Yeah. Until the next, sampler. Okay, combine those. After the combination of these blocks, then you change the S to Z. Okay, for the combined one. Okay. Yeah. Then change the S function to Z function. Okay. Okay, so I'll give you an example now, and see if you can make use of what we just listed here to derive the closed loop pulse transfer function. Alright, so here is the closed loop sample data system. What is the closed loop pulse transfer function for this one in here? Okay. Yeah. Follow the steps. First derive the continuous one, and then observe the locations of impulse sampler. Okay. So try it. So first of all, continuous system transfer function. What's continuous system transfer function? The numerator is always basically blocks on this router here, right? And denominator is 1 plus. This is G1, G2, G1 of S time, G2 of S time, H of S. Okay, yeah. Okay, so what's the closed loop impulse transfer function? There is a impulse sampler here, and there is an impulse sampler here. So if you look at this block right here, this one I can change that to Z because there's nothing else but H of S here. So bottom here, basically, what do we do with this portion, basically, right? Yeah. So according to the rule, G1 of S, G2 of S, H of S here. H of S, G1 of S, between these two, what do? You combine them, right? Because there's no impulse sampler here, okay? However, G2 of S standing out itself because it's separated, right, by this impulse sampler here, okay? So what you do is basically the G2 of S can be changed to Z function directly, but then you combine the G1 and H together first, right? So G1 H, combine them together, then you change it to the Z. Okay. So that's the impulse Z transfer function for this one here. Okay. Yeah, it's much simpler, but of course you have to get the closed loop transfer function right first, right? Yeah, if you get this wrong, then okay. Yeah. Otherwise, you know, you can always going through the loop. Basically, this is E of S, this is E star of S, right? So what's E of S? Is this R of S times this signal. What's this signal? This signal is this G2 of S times and this signal. So you put in this case here, you're going to have put a signal here. You can call that I don't know, M star of S, whatever you wanted to call it, right? Yeah. So basically, you go over the loops, okay, by properly labeling the signals at each location, right? Okay. Then you combine these things together, find the ratio. Okay. So you should get the same result. All right. So any questions? All good? All right. Good. So I have an example, but I think I'm going to skip that. It's pretty simple. Okay. Yeah. Basically, the other example, you can take a look at the lecture notes. Is essentially what happens is just simply based on this one here, I'm adding digital controllers in front of this block. Okay. Yeah. So here there's no control, right? There's no control basically. Okay. So if I add a digital controller here, now what will be the discrete pulse transfer function? Okay. So take a look at that example. Okay. Okay. So next topic. Discrete equivalent. Okay, discrete equivalent. So this topic is more or less actually it's a sort of a numerical approximation, okay, as you're going to find out. Okay. But here's the idea here. Okay, here's the idea. The question is essentially boils down to this one here: how to design a digital controller, or how to come up with a digital controller. Okay, yeah. Now, if the question is, how do you come up with a continuous time controller? Then your answer will be, okay, so I need to come up with a model of the system, let's see, right? And then I'm going to design my continuous system based on the model. Okay, yeah. So here's the same thing. Okay, if I want to design a digital controller, I guess I still need the model, right? You can argue, but this model, right? If you design a digital controller, then this model cannot be the same as the continuous model. So that continuous model, because continuous time, right? You know, but when you design a digital controller, it's all discrete, okay? And which is basically what we're going to learn. Okay, so I probably have to transform the continuous model into what? Into a discrete model. Okay, yeah. So this is basically one thing that we're going to learn in the future. So if you have this continuous system, okay, continuous system, we're going to discretize that. Okay, we're going to discretize it, and then you get a discrete model. Okay, you got a discrete model, right? Then from the discrete model, and there are different mathematical methods. Okay, we can look at the state space model, and then you design, right? Then you design your digital controller. Okay, so that's one way of going it, huh? Yeah. For continuous system, I mean, you can always basically you do a design here, you get a continuous controller. Okay, whatever control algorithm that you use, PID or LQ or whatever you wanted to use, right? You can always come up with a continuous controller based on the continuous system. Okay, and as a matter of fact, you know, digital controller did not show up, right? What shows up first is always what? The continuous control design. Okay, so the continuous control design has a vast, you know, basically literatures in terms of design. That makes sense, right? Yeah. Now the question is, if I'm just lazy here, you know, I don't want to go this step here. You already had this continuous controller here, right? How can we not go in this branch and just going from here directly give a digital controller? Okay, yeah. And from here to here is what we call this discrete equivalent. It's basically what we call it's an emulation. Okay, it's an emulation process. Is that good? Yeah. So let's say, for example, you already had a PID. Okay, the PID is designed based on this continuous model. You had this, you know, all the gains or whatever, right? Yeah. And all we need is we want to come up with a digital controller, right? This equivalent part. Okay. Now that's the process, emulation. And this is what we're gonna, and this is the process here. We're gonna look at it. Okay. Okay. And this process we'll look at it later. Okay. Yeah. This process. Okay. So before we move on in here, well, anyway, we don't have to skip this one here, so we'll talk about it later. Okay? So let's see, what's the emulation process here? Let's see, here is one sort of a not so ideal control, but maybe it could be one of the control here. Okay. Let's say I have y of t equal to this. This is error. Okay. So for this simple integration operation, so we're integrating the area, for example, right? You know, that basically can be the PID, the I part, right? The integration, okay? Yeah. Okay, so we know that the Laplace transfer function, okay, Laplace transfer function for this simple system, input output, is 1 over s, right? It's 1 over s. Okay. So the whole idea of the emulation, okay, this from here to here, from this simple controller to this one, from this simple controller to the digital one here, should be this emulation process. Is what we call the approximation process. Okay, approximation. Okay. So now you gotta forget about all the controls now. Just focus on the math now, right? Focus on the math. So what's this integral here? We know the integral is what? Okay, this is E of t. So we're integrating the integral from 0 to t. Basically, we're looking at is the area, right, underneath the curve, right? Okay, yeah. Okay, so I'm trying to approximate that area. And there are different ways of approximating now. So the first one here, so let's look at it. It's called trapezoidal. Okay, the trapezoid approximation. Okay, and it's also called Tusting's or bilinear's method. Okay. Okay. All right. So how do we use this trapezoid thing set here? So this is what happens. We're going to separate this. Okay, this is a t, 2t, okay, kt minus t, and kt, like this, okay, into a time instant, okay, by sampling time. Then going up for each instant here, okay, you have a moment at here. Then between 0 and the t, we can approximate the area using a trapezoid. This is a trapezoid here, right? Between t and 2t, we can approximate using this trapezoid. Between here and here, okay, you can use another trapezoid like this. Okay? That's called trapezoid approximation. So the area of which is the yt at here now, essentially is the addition of what? All of this area of the trapezoid here, right? Okay. But we're not going to add all of them things there together. But let's try this. I'm looking for the area up to kt moment, right? Looking for area up to the kt moment. But I think what I'm going to do is I'll separate this into two portions. One is the area from 0 to kt minus capital T moment. Okay? Yeah. So basically the area from here to kt, right? K capital T minus T, from here to here. And all you're left with is just plus this guy here, right? And that's plus what? Plus the area, trapezoidal area. Okay, plus this area, the trapezoid, okay, from kt minus t to kt. That makes sense, right? Yeah. Okay. First integral. If y of kt is the area from here to here, then for the first integral, it actually should be what? Just y of kt minus t, right? Okay. Then the area of the last trapezoid, what's the area of trapezoid? It's this side plus this side divided by the height, right? This side plus this side multiplied by the height divided by 2. Okay? So height is how much? T, right? Capital T. Okay? And what's this side height? It's E kt minus t. And what's this side height? E kt. Okay? Yeah. So then area is E kt minus t plus E kt over 2 and times the height, right? T. Okay? Right, so this side plus this side times bracket times t divided by 2. So now you see everything in terms of what now? The key now, right? This is the approximation now, basically. So what are we looking for again? Remember, it's y of z over e of z now, right? Yeah. So it's approximation, right? So let's say now in terms of approximation, let's just say y of z here. Now I'm going to take the z transform. Take the z transform of both sides of this. Okay, z transform of both sides. So what do we have? This is just a one instant delay. Yep.
Okay, I get the E of K of T.
Oh, sorry.
Oh.
Huh? Did I miss the capital T, right? Yeah. Okay. So take the z transform. The first one is just one delay. And then over here, it's E of z times one delay, and then E of z, right? Like this. Okay. So combine them together, you get the ratio. Okay, and the ratio is t over 2 z plus 1 over z minus 1. Okay, that's the ratio. Is that good? Yeah. So you need to bear in mind what we're doing here. It's the emulation, right? Emulation. What is the original one? It's 1 over s. Okay, so this 1 over s representing is that operation, right? So this 1 over s through this Tusting's approximation, or the trapezoid approximation, that 1 over s in terms of the discrete one becomes this. Okay, so 1 over s, you know what 1 over s is? 1 over s is representing the integral action, right? It's integral action. So the integral action in terms of z, or difference equation in terms of z operate the z function, what equivalent integral action? This one. Okay, this one. You know what I'm saying? So basically, you know, in your continuous system, you put an input output, you get an integral action, right? If in the discrete signal, you put a discrete signal into this block, what's out of that block? It's integral action. Okay? Yeah. It's approximate integral action, okay? It's not exactly the same as this. Okay, so that's the first one here, right? Second one here, I think actually I went over this second one a little bit in the introduction of the, or maybe not this one. It's the forward. Basically, there are two. One is the forward and backward. So let's just talk forward, maybe separately. Yeah. So forward approximation. So what is forward approximation? Let me draw it here. So same error function. Okay, you're integrating it, right? Then we have t, 2t, kt minus t, and kt like this. Okay, yeah. Okay. So forward basically means when we are taking the area. So this is what happens. Okay, you are taking a rectangles like this. Okay, so from that moment going forward up to the next moment. Okay, that's forward approximation. So now you actually can think, what's a backward approximation? Basically, not starting here, but if you go backward, it's capital T, you draw a rectangle going backward, right? Yeah, that's backward. So let's just go over this one here, and then we'll just draw the conclusion for backward. So similarly, if I'm looking for the area up to the kt moment, I separate this into two portions. So first is the area up to this moment, and the last area is the rectangle. So the rectangle, which is e to the power of kt minus t times t, right? Times t. So this is e to the power of kt minus t times t. Okay. Take the z transform of both sides. We get y of z over e of z equal to t over z minus 1. Okay, t over z minus 1. So that's a forward approximation. So basically, for the same integral, right? For the same integral action, if you use this approximation, this numerical approximation in approach, then your z block is this. Okay, so that does approximate the integral action like 1 over s. Is that okay? Yeah. So now backward, last one, backward. Okay. If you do that, you'll get okay, you get this. So that's backward. So that's the three different basically mapping or different approximation approach, okay, for emulation. Okay. So this is approximating the integrals, right? Approximating integrals. So how do we approximate a derivative action? You know, in PID you have a derivative action, right? A derivative action, what's a derivative action in terms of S block? It's S, right? And one was the integral, the derivative is S. So if I want to approximate the derivative action, so technically the three things, what do? Just reverse the, take the inverse of it, right? Yeah. Is that okay? Yeah. So we can, I'll just write down one here. So for example, S, right, will become, what do is you replace S with z minus 1 over zt. This is backward. Okay, it's backward. All right? Yeah. Okay. Okay. So I wanted to show you an example quickly here. Then I'll talk about a little bit mapping in the next lecture here. Okay, next lecture. So. Remember that function c to d, right? Remember the function c to d, and then you have let's say continuous one gc, and I said if you put imp here, remember you put imp here, you get what? You get that impulse, basically whatever's in the table, right? I give it to you. And if you put this 0h at here, okay, what do you get? You get there's a zero order hold in front of the block, right? Yeah. And if you put this one here as, now what we call it as a testing. Okay? So you basically get what I just showed you there. Okay? What do? Basically the S is being approximated using testing method. Okay? Yeah. Okay, so now very straightforwardly, if you're going to design a PID controller, okay, yeah, a little bit tight now. So discrete PID. So we might have to go over this next lecture. So if I have a discrete PID here, but I'm going to basically I'm not deriving it, okay, from scratch. So we're deriving it from a continuous PID. So for continuous PID, we know that the general formula, let's say, is this, right? So k times the error plus, okay, this. Okay, so that's a continuous one, right? That's continuous. Okay, so then all I need to do is to do the emulation process to find discrete, which is the z function. You know what I'm saying, right? So, which means what? This block right here, that's basically 1 over s block, and this block here, that's basically the s block here, right? So now you get 3 different choices. So what do I replace? How do I replace the one? How do I approximate this 1 over s block? And then how do I approximate this s block? Okay, and you can. It's actually up to you. You can use anyone. I'll show you next in lecture in MATLAB. There's a PID tool. You can select any one of 3 for this, or any one of 3 for this. Okay. So let's say if I decided to choose trapezoid for this 1 over s here. So for this block here, what happens is I'm replacing this block with t over 2, 1 plus this, and 1 minus this. Okay. And for this s block here, let's say if I decided to use backward difference equation, then for this block, actually all you can do is just replace this with this. Okay? Yeah. So that's the emulation. So then you end up with basically everything is going to be just in terms of z now, right? In terms of z. All right? Yeah. Okay. So I'll show you a concrete example in the next lecture regarding discrete PID and how do you tune. That's actually the first thing you're going to be able to use to implement on the experiment setup, okay, in the engineering lab. Okay. So having said that, on a note of that, so we are actually going to have to arrange a time to go there and take a look at everything. I'll explain it to you. How would you do the project on the experiment setup? Okay. And because there are only 2 mechanical students, for those electrical students, you haven't seen that yet, right? Yeah. In the last year, what I did is I used the class time because it's very hard to find a common time, outside the classroom. So we'll probably just spend 30 minutes there and talking about that thing. And I'm gonna walk back and then continue the lecture. Yeah, last year my lecture room is in the same building as EME, so which works perfect. But this year. Yeah, yesterday I was trying to change the classroom, but